So now the third example, it says here a carpenter is to cut an isosceles triangle out of a sheet of wood, and that triangle is to fit into a corner of a room that looks like this. So presumably there's some horrible hole in the corner here, and he just wants to block it up with this triangle. And he's measured from O to A is 5 centimeters, from O to C is 5 centimeters, and from O to B is 20. So that length is 5, that length is 5, and that length is 20 at the back. And it's asked us now to find the size of each angle, presumably so that he can use a piece of wood to cut it out. So the first thing to do, I think, is to find the lengths AB and BC. And we know that they are equal because it's isosceles, so I'm just going to mark that like this. How would we find the length AB using our information? Well, looking at the triangle AOB, then it's just the hypotenuse of that, and that is 5 squared plus 20 squared, all square rooted. So then AB should be 5 squared plus 20 squared, all square rooted. And that is the square root of 425. So we know now that the length AB is root 425, and I'll add that to my diagram, 425. And it's the same on this side. There you go. And how can we use those two lengths to find AC? If we find the lengths of all of the sides of this triangle, then we can find the size of each angle using a bit of trigonometry. So we can find the length AC from this as well somehow. And the way to do this, I think, is, we can use the base, AOC. So the length AC would equal 5 squared plus 5 squared, all square rooted. Which is the square root of 50. Cool. So, to find the angles of this now, I could rewrite or redraw my triangle ABC with all of the pertinent information on it, square root of 50 and the square root of 425. So how could I use that triangle then to find these angles? I could use the cosine rule, but there isn't a simpler way of doing this as well, and this is just using normal right-angled trigonometry. So by cutting this into a half, I can get a right-angled triangle from that, and then it could be simpler. So I'm going to call that point there M for midpoint. So then by drawing the triangle again with M on it, so that's M, B, and C. This length here would be the half of root 50. So that could be root 50 over 2, and that length up the sides, root 425, still hasn't changed. I can use these two lengths now to find this angle, and that angle is the same as this angle, which is one of the angles that it's asked me to find. And because it's isosceles, I know that it's also equal to that one over there. So what is the length then, the angle from BCM? So that's written like this, angle BCM. And that is, I'm going to call theta. And from the triangle I can say, if I've got I'll do this in a different colour, let's choose pink. I've got here that's opposite the angle. This is adjacent to the angle, and that's the hypotenuse. And I've got a problem involving the adjacent and the hypotenuse, so that would make it a cosine. So I've got cosine theta will be the A over H, which is root 50 over 2, all divided by root 425. Notice I put the the numerator fraction with a slanted division sign, and that's just to avoid the confusion with the larger fraction here. To find theta, I just need to inverse cosine on both sides, and that looks like this. It's the cosine minus 1 thing, and rather than writing out again, I'll just do the dot dot dot, and I can type that all into the calculator, and that should be, I should do this as an approximately equal 80.1 degrees, and that would be to 3SF. So that is the angle here. It's the angle BAC. So what about the other one? That length, sorry, that angle there is 80.1, and so is that one, 80.1. And to find the top angle, of course, I just need to do 180 degrees minus these two. So that means the angle ABC would equal 180 degrees minus 80.1 from one of them minus another 80.1 from the other, and that would be 19.8 degrees. There you go. Now you can start work on the exercises.